Okay, off we go. Let's see here. Last time we were talking about triple integrals, and today we will continue with triple integrals. Remember, the big idea is that sometimes you have an accumulated quantity that is not just, it doesn't add up over an interval, it doesn't add up over a two-dimensional region, it might add up over a three-dimensional region, right? And a double integral is just not going to cut it for that purpose, and likewise single variable integral. So the tricky part very often is in how you turn a triple integral into an iterated integral. It's a slicing process, not terribly different qualitatively from what we do with double integrals. It's three-dimensional pictures, and it's hard to visualize, and it's hard to draw, right? And so it's just a little bit more challenging and very handy to have this other point of view, this projection point of view that I pushed really hard yesterday. So here we go. The last example. Suppose we have a region bounded by two surfaces, and you're going to note quickly that this surface you'll recognize from Chapter 2 discussions is that thing. This surface, again, Chapter 2 discussions, is that thing. And so the thing that's bounded by, the thing that's enclosed in between these two surfaces is a little hard to visualize, right? These two paraboloids, well, they intersect on this circle over here. And so they enclose a volume in between them. And naively, I'm going to sort of do like this and say, well, there you go. It's what's kind of in between them like that. But this is a poor picture because there's actually some solid over here, kind of next to what you might call the edge here. So just to the left of the edge, there's some solid there that's in between the two paraboloids. But if I color it in there, it makes it look like I'm also including this indentation, kind of, and if you sort of go through the circle, there's a hollow section there, right? That's not part of our solid enclosed by these two surfaces. So it's hard to draw a really good picture of it, and that's challenge number one. So here's the next challenge. If you start slicing this thing up, notice how the art gets pretty ugly pretty fast. I'm going to try to draw a Z-slice just for the dramatic effect of it all. And the Z-slice would be something kind of like that. And you really got to use your imagination there to figure out, to persuade yourself that this is actually what that looks like. And it's easy to get this wrong and draw it wrong. And if you make that mistake, then you will mislead yourself with your own picture, and this can get off the rails pretty quickly. So this is a great example, I think, of a good reason to use the projection point of view, because hard though it is to draw it, I think it's pretty easy to see that it's shadow in the XZ plane. It's projection into the XZ plane. It's just a disk. Right? Does that seem reasonable? Everybody kind of buying that? And then also, for any given point, we could imagine now some point here. Let's say something about right there. For any point in that projection, I can say, okay, well, let's talk about as I go in that direction. And I think it's pretty believable that we're going to enter our solid, let's say at a point about like that, which of course is, and again, geometric appeal, but I think pretty clearly always going to be on this surface, which has that equation. Everybody believe in it? And then we're going to exit our solid when we get to that sort of ending point, which again, geometric appeal, I think is always going to be on this surface, which has this equation. So we have the convenience of a nice projection. We have a consistent lower bound surface, a consistent upper bound surface, and a couple of details to work out what are the bounds that come from the shadow, and how do I solve for y on the blue surface and the red surface. We're thankfully already solved for it. Isn't that nice? A couple of details, but basically it's kind of all downhill from here. Is everybody happy with that? Everybody see how I chose to look at this? Okay. All right, so so those rest of those details, let's see here. I tell you what I'm going to do. I'm going to go full screen and get a little bit more on at once. And details for y'all to persuade yourself of. The ZX bounds that you get by looking at the ZX projection, literally two-dimensional. You can think of it anyway as being two-dimensional. Make sure that you can do the sort of double integral slicing of that. Persuade yourself of those bounds. And then likewise, that the blue surface, the blue surface gives us that. And this red surface gives us that. Okay, so that'll do it for triple integrals. And moving along to section 5.5, this is a gigantic section. This will take us at least 3 full lectures to finish. That's the best case scenario, I think. I'm prepared for it to take 3.5 or maybe even 4. We'll see. I think this should be broken up into at least 2 sections. If it were me, it would be 3 separate sections. But anyway, doesn't matter. It's just organization. Content's content. Who cares? Okay, so we're going to talk about a method called change of variables, but we're not going to go straight at it. We're going to start by talking about something y'all have seen long ago called the substitution rule. Some people call this U substitution. There's nothing magic about the letter U, right? So, anyway, I'm just going to call it the substitution rule. And there are different ways to think about the substitution rule. Many reasonable ways to think about the substitution rule. I'm going to give you a particular point of view on the substitution rule. And again, y'all have heard me do this several times. My purpose here is not to teach you single variable calculus. My purpose is to establish a certain point of view, because that's the point of view that I think will generalize most naturally and powerfully in the multivariable setting that we're about to go into. So this is setup purposes. Think of it that way. Okay, so y'all know that when you do a substitution, there is a corresponding substitution function. And for example, here as I have it set up, x is some function of t. And, very often we think of this as an equation, but I'm going to choose to view this as one of the variables as a function of the other. So thinking of it as a function. Okay. Modest observation. If you put a point into this function, then there's an output point that comes out of the function, right? Of course. I mean, in some sense, that's what we mean when we say points go that way. That's why we draw the arrow that way. Is when you plug in a point, it starts on the left and it ends on the right. The function goes to the right. Okay. All right. We'll come back and talk about that again in a second. I'll point out that I could take all of the points in an entire interval from A to B. I could plug all of those in. And all of them would give me outputs, and they would output a different interval on the x-axis, starting at, let's say, G of A, and ending at G of B. Right? Does everybody believe in that? All right. Okay. So let's see here. If we have an integral defined, you'll see here defined on the interval from G of A to G of B. The question is, can I use this G function to somehow rewrite that? Maybe I could rewrite everything in terms of T. And of course, we're just going to be doing a substitution, nothing more than a substitution. And I think y'all remember the answer on this, almost certainly. So here's the answer. The answer is that integral we can rewrite in terms of t with that expression. And a lot of people would just label this as this is the substitution rule. The substitution rule just says that these two integrals are equal. And again, that's fine. Sure. Does that look familiar to everybody? Everybody's happy with that? Okay. By the way, very often when you see the substitution rule, it's a statement about antiderivatives. Here, I've written it as a statement about integrals. Remember, these are different things. An antiderivative is a function. An integral is a number computed by a Riemann sum. Not the same thing. Right? They're very closely connected. That's what the fundamental theorem is all about, right? But an integral and an antiderivative are fundamentally different kinds of critters, and you can't conflate them. The fact that they are closely related does not mean that they are the same thing. So you've got to be really careful about that. Okay. Excuse me. So, all right, two things about this that I want to emphasize. One is what I like to call the pullback aspect of things. And it's a little bit weird, but remember we talked about the function as going this way. The function takes t values from the left, it returns x values on the right, points go that way. Right? That's what we think. Again, that's why we draw the arrow in that direction. The weird thing is that that's not how expressions work. If you take an expression that is in terms of x, you might say an expression that's happening over here in the x-axis. This expression, when you plug in, I mean the act of plugging in, hey, everywhere I see an x, I'm going to plug in g of t, that turns our expression in terms of x into an expression in terms of t. So expressions go backwards. A function that goes to the right, expressions will then go to the left. Everybody see what I mean there? Just for possible clarity, here is a simpler example. Forget about integrals. Let's just talk about regular old functions. And let's suppose I say x is t squared. Right? Okay, well, what can I say about e to the power of square root of t? Can I use this function and can I take this expression and push it forward? I'm going to say as is, not really, because I would need to be able to plug in for t, in which case I would need to be able to solve for t, which it certainly is not currently. We could quibble about whether I can solve for t. I would point out that there's a plus and a minus, and that's a worry, right? But it's certainly as written, not yet solved for t. This function as written does not allow me to push this expression forward. But I can take this expression, let's say, I don't know, sine of x cubed, and this I can pull back. Anything that's written in terms of x, I can pull back, because all I've got to do is kind of recopy it. And anywhere I see an x, I plug in this function that tells me what x is. Does that make sense? Everybody with me? It's a little bit weird. I know y'all have been doing algebra for years and years now, right? And the act of plugging in is not unfamiliar, I presume. But a little bit of a weird take that I may or may not have seen it before. Functions push points forward, they pull expressions backwards. And that's going to be a important point here. So this is what I call, again, the pullback feature of this substitution process. An integral on the right, the act of plugging in turns that into an expression, an integral that's on the left. Okay. All right, here's the second thing that we need to talk. Oh, by the way, that plugging in process. Oh gosh, let me do this in the highlighter. This plugging in process, plugging in x equals g of t. There it is, literally happening. That's nothing more than plugging in. Okay, the second interesting thing happening here. How are we going to think about this g prime? And there's a particular point of view I think is really nice. And again, there's different takes, different ways to think about it. I'm not detracting from those, but I want to think about it a particular way for our selfish purposes coming up momentarily. Let's talk about dt. dt represents the size of a little interval, let's say on the left. Now, what happens when you take those values, all of these values, and you plug them in? And, well, what happens is a bunch of other values come out, and that gives you an interval on the right of size. I'm going to call it dx, because that represents a little piece of the x-axis. So dt gets turned into dx. They're not the same. Right? This function g, maybe this function g, maybe all the numbers get multiplied by 7. Maybe, right? Then this interval will be 7 times as big. They're definitely not the same size, generically. Okay, so how can I think about the relationship between the blue dt and the green dx? And I'm going to make the observation that we already have that relationship. We already know that dx is g prime times dt. That's just a derivative. That's what a derivative does. Right? Derivatives are what you multiply by input differentials to get output differentials, in this case. All right, so that's the way I want to think of this g prime right here. I want to think of it as the thing that tells you by what factor does this size get stretched out to produce this size, and thus the term stretching factor. Which I'm not the only one using this term, by the way. I wouldn't quite go so far as to say it's universal, but it's everyone knows what you're talking about if you say stretching factor. What do you think? Everybody buying it? Okay. So, again, the purpose of this is not to teach you Calc 1, or Calc 1 or Calc 2, whenever this gets covered. My purpose is to set up a particular point of view so we can look at how that extends to a multivariable setting. And here we go. Here's the two-dimensional equivalent. We start with a domain on the left. We point out that if you plug all of those points into whatever your function g is, I don't know, whatever that function is, you're going to get a bunch of points that come out. And by the way, that g function might be weird. So this output shape might not be nice. It is what it is. And in this scenario, we have a, let's say a nice domain on the left and a maybe less nice domain on the right. Let's suppose that we're interested in computing an integral on this domain on the left, right? And let me remind you, here was our single variable equivalent. We were looking at an integral on this domain on the right side. That's sort of the output domain. We had an integral on that output domain, and the substitution rule says, yeah, that's an integral on the original input domain. And just, you basically plug in and insert your stretching factor. So the exact same thing works here. I can take that integral on the right, and again, as an expression, expressions pull back. The result is an integral on the left defined on that original domain. And all I got to do, two things. Don't forget to plug in for x and y. X and y are g of u and v. X and y are formulas. X and y are the outputs from g. X and y are literally formulas in terms of u and v. So plug those in. And then just don't forget, let's see here, let me recover some colors here. Don't forget that the size, du dv, and the size of its image, dA, are not the same, and there's going to be some factor that I multiply by du dv, some factor that I'm going to call the stretching factor, to produce the stretched out area in the xy plane. What is that SF? What is that stretching factor? Oh gosh, well, we don't know at the moment, but there will be some factor, and it turns out there's a nice formula for it that tells us how much does area get stretched out by this function. So strategically, structurally, it's just like the substitution rule. At least it's just like this particular take on the substitution rule, just apply it in a two-dimensional setting. And again, the punchline is that this is a formula that tells me how to solve a really hard problem. Inadvertently, we've solved a really hard problem. If you have a domain that you don't like, right, that's your domain, and you need to compute an integral on that terrible domain. Yikes, what are we going to do about it? Let's take a moment. This is a terrible domain, right? As you go through your slicing through corners, you're going to have to end at some point on the right way over here. So 1, 2, 3 corners at least. I mean, this is not good. If you need to compute this integral, if you can figure out how to view that as the image of something else that you like. Now, how to do that? It's a trick. We'll talk about that, right? But hypothetically, if you can find a way to view your ugly domain as the image of something nicer, then you can just wave the magic wand and say, pull back, right? Then you're going to have a new integral defined on our pullback domain, a much nicer domain, and all you have to do is plug in, and don't forget to insert that stretching factor. It's an amazingly powerful result. If you can view your domain as being an image, it's a couple of quick little bits of algebra to do the pullback. Okay. All right. Now, we're going to do an example momentarily. There is the remaining matter of I haven't yet told you what this stretching factor is. I'm going to write down the formula. Deriving it is not that hard, but we've got a lot going on as it is. I don't want to get distracted into the weeds of how do we prove what that formula is. So I'm just going to write it down, and here it is, the formula for your stretching factor. For the moment, take my word for it. It's the absolute value, which is annoying, right? We don't like absolute values, but we have. It's an important part of the formula. Absolute value of the determinant of the derivative matrix. That's it. And you all know how to compute derivative matrices, you know how to compute determinants, and you know how to write down absolute values. So it's very plug and chug. It's just a matter of writing it down. Okay. Now, a quick reminder, don't forget the derivative matrix is made up of those partials. Make sure to get them in the right places. And then here's a notational shorthand. I find this really convenient. I really like this a lot. The determinant of the derivative matrix, not the derivative matrix itself, not the absolute value yet, right? So just the determinant of the derivative matrix gets rewritten like this. It writes it as if it's a fraction. Now we'll take a moment to recognize that's a bunch of nonsense. It's not a fraction. Look at it. It says right there it's a determinant. Determinants aren't fractions, right? It's just not. But we're going to write it as a fraction, and the reason is that it behaves very much like a fraction in a couple of really valuable ways. And the first one of which I will show you right now. Let's see here. Okay, so let's look at what we have on the left here. let me write it a little bit bigger. du dv multiplied by our stretching factor. Let's see our stretching factor. Here it is, absolute value. I'm going to use this notation, partial xy, partial uv. Now, and I cringe as I do it, because this is a bunch of nonsense, but it's satisfying and believable nonsense that will always lead you in the right direction, so it's extremely convenient. It's almost like this thing with u's and v's cancels with that thing of u's and v's, thus leaving us with a thing with x's and y's, which you might reasonably interpret as representing area in the xy plane. Now again, that's not fair. That's not legal algebra. This denominator that I canceled with the du dv, I haven't even defined what that is. It's not a thing. This is not a fraction. There is no cancellation. This is all garbage. But it sure is convenient garbage, and again, it will always lead you in the right direction. And so for that reason, I encourage it. Right? Just don't believe in it too much. Okay. All right. How we doing? Is everybody on board? Got an example incoming? Okay. Here we go. All righty. So we have, let's see here. We're going to start with the unit square and the, oh gosh, hang on. I wanted to be in the highlighter mode. Unit square in the xy plane given. We're going to apply this function. That function gives you x and y as functions of u and v. That therefore is a function that goes that way. And now let's think through what happens if you take all of these blue points and you plug them into some function. Well, you're going to get some set in the xy plane as the output. That set in the xy plane happens to look something kind of like this. Excuse me. And that is to be our domain for an integral that we want to compute. And the question is, how do I compute that double integral? Double integral over this green domain. How we is everybody seeing the statement of the question? Everybody with me? Any questions so far? Okay, now real quick, let's get rid of this and this. I'm being asked to compute an integral on a domain, and I'm going to go ahead and say this is an integral on a domain that I don't like. I don't like this domain at all. Whichever way you slice, dx, dy, or dy, dx, you're going to hit two corners. So if I write this as an iterated integral, that's that innocent-looking integral up there. As an iterated integral, this is going to be three separate iterated integrals. Already I'm not happy. And then I will also point out, in this particular case, of course I'll need to know the equations of these curves. I'll need to know how to rewrite either y as a function of x or x as a function of y. I don't have that. I would have to figure out how to manipulate algebra around in some way with these expressions to infer some relationship between x and y, and it's not obvious how to do that. You can do it, but it's really not obvious. Everybody see the problem there? So this is a hard problem as written. Okay. All right. Well, let's keep in mind our tool here, our big tool, is that if you have an integral defined on a domain that you don't like, all you got to do, figure out how to view it as an image of something that you like better. That's it. Just figure out how can you view that thing as an image, some function, you got to know what the function is, of a domain that you like better, and you got to make sure that you can deduce what that pullback domain is also. So can I do that here? Well, yeah, not only can I do it, it's been done for me. In fact, our domain here was defined as being the image by way of a given function of a given domain. So this is ripe. This is set up as fully ready for us to do the pullback. Everybody with me? Okay, now let's look back at our formula here. When we do our pullback, we're going to need to do two things. One is I'm going to have to figure out how to rewrite x and y in terms of u and v, but that's just g. That's my pullback function. That's already given. I already have that. So that's not a problem. And the other thing I'm going to have to do is I'm going to have to compute my stretching factor to be inserted like so. And how do I compute that stretching factor? Well, okay, I'm going to have to compute the derivative matrix, take that determinant, take the absolute value of the result. That will be my stretching factor. So here we go. Let's do it. Again, here's my G. Here's the derivative matrix, sometimes called the Jacobian matrix. Reminder. Make sure you can do this, of course. Right? We talked chapter 2, how to write the derivative matrix, various partials assembled just so. Right? Make sure you assemble it correctly. So there's your derivative matrix. It's easy to compute the determinant. There you go. Nothing to it. And then the last step, and this is a little bothersome, but I do have to take the absolute value. Again, that's part of the formula. The stretching factor is the absolute value. You can't just kind of blow that off. That's non-trivial in the situation. So now I've got to figure out, how do I take the absolute value of this Jacobian determinant that I just got through computing? How do I find the absolute value of 4uv minus 9? And at a glance, this looks like oh gosh, what am I going to do with this? Is there some algebraic trickery that I can pull that will help me? And it turns out there's a different approach to take on this, and that is to understand what are u and v in the first place, and take what we know about u and v and then deduce accordingly. And here's how easy that is. What do I know about u? I actually know a lot about u. I can see, right there in my picture, I can see what u is doing. On my entire pullback domain, u is always between 0 and 1. So I don't know exactly what it is. It could be any number. It's going to eventually be all the numbers between 0 and 1, but it's always between 0 and 1. And then likewise, v, well, again, there's v in my picture, and check it out. It is always, in this case coincidentally again, between 0 and 1. How are we doing on that so far? Is everybody see where so I've drawn some conclusions about u and v by looking at my pullback domain. And now it's kind of all over with the shouting. U and v are always between 0 and 1. The product is between 0 and 1. 4uv is therefore always less than 4. And when you subtract 9, this thing is therefore always negative. Everywhere in my entire pullback domain that we're going to be doing our pullback integral on, this expression is always negative. Does that make sense to everybody? Everybody see the argument there? And I hope y'all also recall that the absolute value, this sounds weird when you say it, the absolute value of a negative number is the negative of that negative number. Does that sound right? So that makes our absolute value 9 minus 4uv. Everybody happy? Cool. All right, and now we're pretty much plug and chug mode at this point. And let's see here, I can do it like this. So reminder, we started off looking at this domain here, right? That was our domain. We don't like that domain. It's full of corners and weird equations, and I don't even know what to do with that. We found a change of variables function through which to pull it back. Now we're going to have an integral on this new domain that we like. It's just the unit square. U and V both 0 to 1, 0 to 1. Very easy bounds. That's kind of the whole point here. And now the only thing left to do is to make sure to, plug it in, and don't forget your stretching factor. Let's write down the stretching factor first. The stretching factor, we just computed 9 minus 4 UV. Don't forget to plug that in there. That's what makes it legal. Right? And then there's the matter of, again, just plugging in. And for example, let's see here, what do I do with this x? Okay, well there's x. X is one of the outputs from the g function. I can see it right here. X is u squared plus 3v. So let me do it like this actually. So x is u squared plus 3v. Likewise for y. How are we doing? Is everybody following? Is everybody happy? Okay, now let's stand back and ask ourselves: was this a win? Some people would say, you know what? Thanks, but no thanks. I'm going to go with the integral on the left. Look how much more short and compact and pretty looking it is. And this integral on the right, oh my gosh, so terrible. It's a bigger polynomial, but it's still a polynomial, and polynomials are just not that scary from an integration standpoint, right? It's got a few terms in it, but whatever. The bounds for this integral are awesome. 0 to 1, 0 to 1. We would write this as a single iterated integral on the unit square. Just could not be nicer. Whereas our original integral, and again, don't be deceived by how the integrand is simple looking. The problem with this is it's defined on this nightmare of a domain with corners and weird curve edges that we don't know the equations for. This integral on the left is a nightmare. This integral on the right is very straightforward. So I'm going to call this a big win. Is everybody with me? Okay, now, confession. This was a highly manufactured and unnatural example because, after all, I explicitly gave you the pullback domain in the setup of the question. And I explicitly gave you the change of variables function. That's not how life works. Right? The fair statement of this question might have been something more like, let's see here. None of this is given. We'll just scratch all that out. I don't know what this is, and just be, hey, compute an integral on that domain. Right, and without that change of variables function given, all of a sudden, how do we get started? Where do I get my change of variables function from? How do I know what the pullback domain is? Right? Y'all are going to have to figure out how to do that to be able to use the change of variables method. So here's the short answer on how we do that. There are limited cases where we can arrange things cleverly and conveniently and use this method. It is not the case that I can just take any domain, however horrible, and just come up with a good G and a good pullback domain and use it. It just doesn't work out that way, right? So don't think in terms of a general process for finding G and for finding the pullback. What we're going to do is we're going to notice how it works in certain kinds of examples We're going to remember the tricks for those limited examples and then try to adapt those ideas to problems as we see them. So this is limited cases where we can make this work. And I'm just going to show you a bunch of these cases. All right, now before we move it along, there are some change of variables functions that are particularly convenient. This translation is particularly convenient. Comes up, and note specifically what that is. That says that if you have some domain, let's say that, and if you want to know what happens to that domain, well, this function translates by the vector AB, whatever AB is, and then my new domain is going to be up there like that. Right, so the change of variables function that I have circled here sort of shifts up and to the right. How will we use this in practice? Well, in practice, we're going to start by having this domain over here on the right and not being happy about it and trying to figure out what am I going to do about this. And I'm thinking, well, wouldn't it be nice if, and then I pick this change of variables function, and what it will do is turn this domain that I started with into, by pulling backwards, this domain that, let's say, I like better for whatever reason, and effectively then, in the pullback, what this does is it translates backwards. What I'm given translates backwards into what I would like to work with. Okay, so you always got to keep in mind the pullback always sort of undoes what the change of variables function does. And so that makes things always seem backwards. Okay, here's an example, really nice example. So let's suppose we have this square as our domain. You can check and make sure you can do this, of course, that those 4 points form a square, specifically a square like this. Yeah? Now again, let's just contemplate for a second. If I were to come at this the old-fashioned way, if I were going to take a 5.2 approach to computing this integral, don't know nothing about change of variables, right? I'm just going to dx dy or dy dx, whichever way, and notice you're going to hit corners. You're going to hit 2 corners, whichever way you slice it. So this is 3 iterated integrals, and by the way, 3 iterated integrals where, by the way, I have not yet figured out what the equation of that line is. I'm going to have to do some annoying Algebra 1 to figure out what the equation of that line is, and likewise, these other lines. Right? So this is a pretty inconvenient approach. The straight ahead plug and chug method on this integral is not desirable. Everybody see how that stinks? Okay. All right, so now the pullback idea, I want to ask, now let's think creatively here. How can I view this domain? I've got this tilted square here. How can I view this as being the image of something I like? Remember, that's our deal. That's how this works. The whole point is your undesirable domain, you want to figure out how to view it as an image of something you like better. So that when you pull back, your new domain will be that something you like better. So how can I view this tilted square as an image? And I think it's a pretty believable thing. I can say, look, this is a counterclockwise rotation of that square. Everybody see that? Now again, you have to worry about the kind of the forwardness and backwardness of it all. The pullback domain, I have to rotate counterclockwise to produce my given undesirable domain. Okay, well, yeah, okay, but another way to say that is that starting with my undesirable domain, the act of pulling back rotates it clockwise to produce the more desirable thing that I like. So again, there's the fact that there is a pullback, the fact that there is a backwardness to this. You've got to keep straight. Which way do I go? Right? And you just have to be careful with that and think it through and make sure to be clear in your mind of which way does your change of variables function go. What's your pullback domain? What's your given domain? And just be careful. All right. Cool. So, a little geometry makes it easy to see that these bounds are 2's. I understand the pullback domain very nicely now. It's 0 to 2 and 0 to 2. Now, what is the change of variables function? This change of variables function, well, it's a rotation. Specifically, it's a rotation by that angle. And now you got to think to yourself, how do you do a little bit of trig and remind yourself of the coordinates of this point and trig this and that? Persuade yourself that angle's pi over 6. And again, that's just a little bit of geometry, a little bit of trig, looking at these points. So pi over 6. Again, make sure you're good with that. And so, okay, no problem. Rotating by pi over 6. Let's again clear out the mess that we no longer need. How do I rotate by an angle of pi over 6? Well, that's a little linear algebra problem. And here's the punchline. And again, make sure you can do that. Now, this is linear algebra. Again, Math 218 or 221, depending on what you took. We talked about this also at the beginning of this course. Hopefully everybody's good with this. And again, I'll hit the very broad highlights. The way you do a rotation is to recognize it's a linear transformation. Therefore, it's a matrix. And the columns are the images of the standard basis vectors. So you just have to rotate the standard basis vectors, do some trig, and this results. Okay, if you have any questions about how to do that, come talk to me. I'm very happy to help. Got to make sure we're all good with how to do that. Okay, all over but the shouting at this point. Pretty much. We do have to compute the stretching factor, but here's our formula for x and y as functions of u and v. You take various partials, blah, 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 and your stretching factor is 1. And don't forget to insert that stretching factor into the into your new integral. By the way, just a point of order, this 1 doesn't make any difference to the answer. Don't forget, the answer is not what we're here for. Right? It's not about the answer. It's about the argument. It's about communicating to your grader what you understand about the argument. So even though this 1 doesn't make a difference, go ahead and be sure to stick it in there. Now the grader clearly gets that you knew what you did here and you didn't forget to insert your stretching factor. Does that make sense? You want to keep your grader happy. Happy graders are generous graders. Right? Okay. And then there's the matter of plugging in, right? So we've done this before, but let's do it again. What do I do with this x right here? How do I get x? Well, don't forget x is one of my outputs. X is explicitly told to me by my change of variables function. And in fact, I can see it right here. There it is. That's x. It is this dot product, which is that right there. All good? All right. So again, we have a matter of trade-offs. There's originally we had this integral. We've done the pullback, and we now have this integral. And which one do you like better? I have a pretty strong preference on this one. This is 3 iterated integrals. It's just hiding because I'm hiding all the ugly in the ugliness of this is in the shape of the domain, which I've swept all that under the rug and just called it D. You know, don't look inside a D. That's where the nasty shape is. Right? This integral, I've been quite explicit about what these bounds are for the iterated integrals, constants. This is a single iterated integral. Doesn't get any nicer than that. And the worst thing I have to say about this is that these coefficients have square roots in them, but they're just coefficients. They're just numbers, right? Nothing algebraically challenging in this right-hand side integral. So this is a way better integral. Is everybody with me? Okay. Real quick. Again, we have a lot going on with change of variables, keeping track of the push forward and the pull back and the stretching factor, and it's geometrically challenging, and how do I figure out the block, all this stuff going on. And so I didn't want to distract from that at the beginning. I will point out that in order for this to work, I do need my change of variables function to be continuously differentiable. That is a requirement. Here's the good news. Every function we're ever going to want to use as a change of variables function is, in fact, going to be continuously differentiable. So that's great. There's another subtlety. It's got to be invertible. This is a longer discussion to justify, but we do need it to be invertible. If you're curious why that is, feel free to come talk to me. I'd be very happy to give you 15 minutes on that, but it's not something that we can do class time on. So anyway, just make sure it's invertible. And again, good news, pretty much everything we're going to do is. Okay, y'all have a great weekend. See you later. See you on Monday.